So good afternoon. Good afternoon. My name is Josh, and this is Joe. And our project was the design of a 4-bar for a hexapedal walker. Okay, so when we reviewed the literature about rocking robots, most of them were just tested in laboratory settings, going in a straight line with like clean, very smooth terrain. So for our project, we wanted to design a simple 6-legged walking robot to navigate around obstacles so it was able to turn, and also over rough terrain such as river rocks. This has possible applications in exploration where it's too dangerous for humans to go. So this could be space exploration, surveillance and combat zones, communication, or search and rescue operations. For the kinematic design of the robot, all 6 legs have the same 4-bar mechanism. And to generate this, we solved the path synthesis equations. So we chose our 5 desired ground points out of all the possible 4 bars that were generated by a Mathematica script. We chose this one because it's compact. The links are somewhat smaller and very close together. And there's also a front lift that you can see at the front, and that's ideal for a walking robot. Our body was designed to have a very low size and weight, so we cut out a lot of holes in the body just to eliminate any dead space, conserve material, and reduce the force that would be on the legs. To put the gears and shafts in double shear to doubly support them, we have columns that you can see on each side, just supporting them, providing a little bit extra strength. The body was also designed to house all the motors and electronics. As you can see, there's in the bottom picture, we have a Beagle Bone Blue board with a battery under it, and then 2 motors, one for each side that powers the legs. So the body compactly houses all of these. It's very efficient in use of space.
So in terms of linkage design, all the legs are the same. They use the kinematics that Josh just described in the previous couple of slides. We modeled it all in SolidWorks with the goal of increasing strength, stiffness, while maintaining kinematic accuracy with all the legs. And with all that in mind, we wanted to reduce size and mass, just make it as lightweight as possible. So on your left here, you can see one leg individually with link 1 as the crank. It goes all the way around. Link 3 is the rocker that just goes back and forth. And then the path that we saw earlier is at the bottom tip of link 2. So in order to increase strength, we wanted to put as many points as we can in double shear, so as many joints as we could. Mostly were slip and press fit in depending on what we wanted. And so double shear, you can see in your far right with numbered 4, it goes out much farther and it's kind of like offset, and there's a gap in the middle where the pin is inserted. So a concern we had with this is because everything was being 3D printed layer by layer, a common failure mechanism is at the layer where the shear is highest. And so because everything is printed horizontally and then constructed vertically, all that force is going up and the moment arm can be very large. So we want to increase that thickness. In terms of assembly, you just saw the left side, and to get the right side, that was simply mirrored and then attached to the body that Josh described earlier. The biggest struggle we were having was just reducing friction overall, as well as improving the alignment and concentricity between all the pins and stuff between the body and the legs themselves. So we tested everything by hand and then by motor just to make sure friction was as low as possible. In the end, I think it turned out pretty well. As you can see in this video, we were able to maneuver through a slalom course that we designed. This video sped up. It took about 2 minutes overall to go back and forth. Another important component of our robot was the ability to turn completely in a circle, do a spin. So one side was going forward, one side was going backwards, and you were to make a complete rotation in about 9 seconds, which I think compared to literature, that was pretty good. In the picture below, it's not quite a video, but we were able to traverse rocky, uneven terrain. And then potential improvements in the future, we kind of want to introduce compliant joints that will hopefully reduce friction and complexity in the assembly process, continuing improving by reducing friction and improving alignment. And then we just want to reduce the gear ratio a little bit because we found it was a little more than needed. And if we have a lower gear ratio, we can go a little bit faster. So thank you. Hope you enjoyed our presentation.
So second